Thanks for the introduction. Hello, everyone. Thanks for coming to my talk. My name is Andong. I'm from the University of Toronto. I'm going to talk about practical type inference with levels. This is a joint work with Han from Princeton University and Ningning, my PhD advisor. So modern functional languages such as Haskell and OCaml, they have advanced static type systems and rely on sophisticated type inference to infer types automatically and become practical. For type inference, there are many formalizations that describe type inference formally and precisely by declarative specifications and algorithmic formalization. With such formalism, people study the theoretical aspects of type inference algorithms such as their soundness and completeness and so on, formally. On the other hand, there exist practical implementations of type inference algorithms, and many of them employ various implementation techniques for good reasons such as performance improvement. However, those implementation techniques, they bring a huge gap between the theory and practice of type inference. Such a gap could lead to, first, confusion for implementers who follow the specification, the formal presentation of type inference, and they could only find more efficient implementation techniques later. And perhaps more importantly, this gap could compromise the theoretical guarantees provided by the formalism because those results doesn't directly apply to the implementation because of those implementation techniques. So this paper, we focused on formalizing one such important implementation technique called levels to bring the theory and practice of type inference closer. So we contribute formalism of a type system that incorporates the following language features: data generalization, local data types, and higher rank polymorphism. They are all within a level-based type system framework. And we provide mechanized proofs of the soundness and completeness results of level-based type system in the ROC theorem prover. We also provide a formalization of a level-based and a bidirectional type inference algorithm. And finally, we implemented level-based type inference for the COCA programming language and evaluated its performance. COCA is a research programming language featuring a type and effect type system. So next, I'm going to give you an overview of our formalism that supports data generalization, local data types, and higher rank polymorphism within a level-based framework. Okay, so let's get started with data generalization. Data generalization is an important aspect of Hindemiller type systems, which is the basis of type systems in functional languages like OCaml and Haskell. Let's take a look at the example here of a let binding in Haskell syntax. Here, we define f as an identity function, and it's bound to the body of this let binding expression after the keyword in. Notice that this f is applied to two values of different types, int and bool. And this f as an identity function, it could be used polymorphically without problem. So how could this be type checked? In Hindemiller type system, when we are typing the right-hand side of let binding, here, the identity function, we assign a type variable, for example, a to x, and give the identity function the type A to A. And let generalization kicks in to generalize this type to a universally quantified polymorphic type for A to A. And now this f can be used at different types because A is a universally quantified one, and it can be instantiated to what type is needed. Okay, so to be formal, the formal presentation of Hindemiller type system is as follows. We first type the right-hand side of the let binding, which is U1 at type tau1. And here, later we generalize free type variables in tau1 as for a dot tau1 and put it in the typing context. Here, there's an important side condition that requires the type being universally quantified. They should not appear as free type variable in the typing context. This check is crucial for the soundness of the let generalization. But in practice, it also causes significant inefficiency because we have to traverse through the whole typing context to compute all free type variables in it. So let's see an example of level-based let generalization with level. The idea was originally proposed by Didier Remy in 1992. So here we have a typing judgment form. Under typing context psi, we infer the type of V as type sigma. And here we have a natural number n, which is the current typing level. And let's check out the simple example. Here we start with an empty context and infer the type of simple program which binds the identity function to f and use it, return it directly in the lab body. So we start with typing this expression at level 0. And here, to type the right-hand side of the lab binding, which is the identity function, we first bump the level number to 1. And after bumping the level number to 1, we are allowed to introduce a fresh type variable a at level 1 into the typing context and say that the free variable x has the type a. And we infer the type of the identity function as a to a. And to type the lab body, here we get back to level 0, and we generalize the type of f, which is the bound polymorphic identity function, and its type is got generalized at level 1 to be a polymorphic type. Polymorphic type for a dot a to a, and we infer the type of f as this type. So with that example, we can take a look at the formalism in our system of level-based let generalization. So to type a let bound expression, we first type the right-hand side of let binding, which is E1 at the level n+1, and it has an infer type sigma 1. And later, to type the let body, we get back to level n, and we generalize the free type variables appearing in sigma 1, and those free type variables are at level n+1, so those are the type variables that got generalized, which corresponds to our earlier example where the type of f was a to a, right? And we generalized the free type variable a because it was at level 1. And why generalizing type variable at level n+1 is okay and enough exactly? Here, we enforce an important invariant that typing contexts always have levels less than or equal to the typing level. So, the type or the typing context psi, it could only contain free type variables at level less than or equal to n. And as another important property, the infer type of sigma 1, which comes out at the typing of the level of typing n+1, and this sigma 1's level can only be less than or equal to n+1. So all the free type variables appearing in sigma 1 at the level n+1, they are free in the context. Okay. So next, we take a look at another the next feature of our system, which is local data types. So consider this example. Here, we define a binary tree data structure that is constructed by leaves of integer values and nodes of subtrees locally. This tree data type is bound only after the keyword in. Here, we pattern match on a node value and return a string on both branches of the match. Overall, this expression returns a string value. And notice that this tree data type is only valid locally after in and not outside of this data expression. On the other hand, if we return a leaf value directly, then the expression as a whole, it returns a tree value which goes out of its scope. So this one is rejected. To model this behavior, we have this in the level-based system where we first put the type constructor T into the context and it's at level n+1, and so that when we are typing the expression E, we can use the type constructor at level n+1 in the E. And here, notice that we again bump the level number to n+1. And in the return type of this expression, which is sigma, we have a side condition that requires this sigma at level at most n, so that it could not refer to the local data type T, which is at level n+1. And this level check on the return type, it could be implemented smarter as is implemented in OCaml type checker. It can be a constant type lookup. Okay. And finally, the last feature of our system is higher rank polymorphism. So as an example, consider a lambda expression where the input is annotated as a polymorphic identity function type. And in the body, this f is applied to both int and bool. And the type of this lambda is so-called a higher rank polymorphic type because there is a universally quantified type for a dot a to a appearing on the left-hand side of the arrow. To type check such a program, we need this kind of subtyping or subsumption relation here, which says that the type sigma 1 is more general than the type sigma 2. And the most important rule in the subtyping relation is these two rules, which compares two polymorphic polymorphic types. The type on the left says that if we compare a type sigma 1 to be less than another type with a universal quantifier, we have to recursively compare the type of sigma 1 and sigma 2. And here, importantly, we need to check that this type variable A is fresh and it does not appear in the free variables of sigma 1. And this check is called the Skolem escape check, which is also crucial to the soundness of higher rank polymorphism. And when the polymorphic quantifier is on the left, then we have the freedom to choose type of tau to instantiate for this free type variable A in sigma 1. And we can instantiate this type to a monomorphic type tau, right? That is in the non-level-based system. In the level-based system, again, in the subtyping relation, we associate the relation with the level number n, and the level number basically says that the relation it could use type with levels less than or equal to n. And the corresponding rule for all R and for L are as follows. And in the when the polymorphic type is when the universal quantifier is on the right, we first, again, type of sigma 1 and sigma 2. And here we again bumps the level number to n+1. And the free type variable A is now at n+1 because it's only usable after we get rid of the universal quantifier. And when the universal quantifier is on the left, when we're comparing for A dot sigma 1 to be less than sigma 2, we are allowed to instantiate this A to a monomorphic type, which is at level at most n, so that it could not refer to the type which is especially a free Skolem type at level n+1. Okay, so our formalism, we provided mechanized meta theory in the rock theorem prover. We have the non-level-based type system, which I just showed you, and we have a level-based type system, which has a level number on that, right? And these two systems are proven to be sound and complete in the rock theorem prover. And the sound and completeness, they relies on key level-based invariants, and the details could be found in the paper. And in the proofs, we reviewed novel level-related properties to prove completeness of of the level-based system, and such as notions of level matching and compatibility. Okay, and additionally, we have a formalization of the algorithmic type system, and in the algorithmic type system, additionally to the term context, we have an algorithmic type context, which keeps track of the levels of type constructors and the so-called, again, Skolem type variables. And we have unification variables in the typing context, which are alpha hat, and they have a level number on that. And the unification variables, they can be solved to monomorphic types as tau. And here, there is another important invariant that the solutions of the unification variables, they could be at most level n. And the result of the algorithmic type system is that we have proved the algorithmic type system, which is a green set of judgment forms. They are sometimes complete to the declarative systems that we proved sometimes complete in the Rock theorem prover. And this result is also under the important level-based well-formedness conditions. So in our paper, we also have done some case studies. We explored the use of levels in the GHC, which is the state-of-the-art Haskell language compiler. And levels, they are, in addition to lead generalization and higher rank polymorphism, it is also used for kind polymorphism and type inference for GATTs and etc. And for OCaml type checker, OCaml has some very smart and optimizes use of levels. For example, in OCaml, types, they themselves directly associate a level, while in our formalism, we only associate levels to type variables, and we have to traverse the whole type to compute the level of the type. And as for our implementation in for the COCA compiler, we have implemented the level-based type inference for COCA, and we, as a preliminary evaluation result, we evaluated our implementation by generalization, which is a benchmark that emphasizes the generalization process, and the generalization is tested on varying type context sizes so as to stress the performance improvement of the level-based generalization. And as you can see, the trend of the performance improvement, where the blue bars are the level-based COCA and the red bars are the original COCA, which has a traditional context traversal approach to do lead-based generalization and scaling escape checks. Okay, so as a conclusion, we have more in our artifact and our paper. We have mechanized proofs and the COCA implementation. They are in the artifact, which is evaluated as reusable. And we have a complete formalism of lead-based systems and very detailed examples of the declarative and algorithmic system in the paper, and the soundness and completeness results. And also the details of our implementation and of the validation and evaluation of the implementation. And thanks for your attention, and I'm happy to take your questions.
So, do we have some questions from the audience? Okay. I have a question. So your algorithmic system, is that also mechanized in the Rock theorem prover?
No.
Can we go back a few slides just to?
Yep.
So my understanding is the soundness and completeness theorems. Do you have a plan to mechanize that, and like what would be challenges that you see to mechanizing your soundness and completeness theorems here?
Right. Thanks for the question. Currently the result is not mechanized, and we are definitely interested in mechanize this system. And as you may know, the mechanization of type inference is actually a bit hard because you have to deal with the binding and the scope carefully in the theorem prover. But we believe that the integration of levels to the mechanized type inference algorithm does not really bring any fundamental challenge, because I think the level numbers, they are more or less as orthogonal concern to the difficulties of mechanization of type inference, I think.
Thank you. And can we look at your benchmarks really quickly? Could you bring that slide up one more time? How did you choose your benchmarks here? From COCA?
So that's a good question. The benchmarks, they were some randomly generated functions, and it's a big top-level function which has some nested little functions inside, and we nest 200 functions in it. And in the top-level function here, we adjust the number of parameters so as we can adjust the size of the typing context to control that, and and we run the benchmark like for 10 times and take the average.
Okay, thank you. Oh, we have a question, please.
Nick Swami, Microsoft. I'm just wondering, we had this talk yesterday from Dan about another kind of type inference, and he was talking about static overloading, and I'm wondering if your level-based system would be able to handle this kind of thing also?
Right. So, right, I think, yeah, so I think dumb system more address the problem of the declarative system, especially when there is absence of principal types. In the system under prefix, we can properly reject those programs without principal types. And I think the integration of levels, they should be mostly, especially static overloading, they should be mostly orthogonal constants, I guess. But if we integrate some other features like the trickier examples of GADTs and even first-class polymorphism, it could be trickier, I think.
Let's thank our speaker again.